So the DESMOS activity you're working on was trying to get you ready to answer this question in calculus. The short answer is there are 3 different ways. The DESMOS looked at 1.5 of those. Okay. So how do you determine the derivative of a function's inverse? And one of the really important things that we need to make sure that we are using is our words, because I saw in your DESMOS activity words like inverse and reciprocal and opposite and all kinds of things, and those mean distinctly different things depending on what you're doing. So, for example, inverse. In the function sense, which is the sense we're talking about, your x's and y's swap. What I mean by swap is they switch. You trade your x's for your y's. So if I have an input of 4 and an output of 5, an inverse would have an input of 5 and an output of 4. Algebraically speaking, using the notation that I really don't care for, F inverse is written like this. So doing exactly what I described, 4, 5 becomes 5, 4 would be like doing F inverse, okay? And you may remember this, probably not, because it was tedious and the very beginning of pre-calc, but you did some algebra to prove that functions were inverses. And the idea was if you substitute F into F inverse and F inverse into F, both of them return X. So what we're getting at with that is this idea. Pretend that you start with X. Okay? Let's pretend we start with X. And I add 5 to X. What's the inverse? The F inverse is -5 because that returns me to X. And the same thing is true. If I start with X and I subtract 5, I have to add 5 to get X. This is the core idea of inverses. This is the function equivalent to what you studied when you're solving equations. If you have an equation, like again, X plus 5, we just say it equals 0. You subtract 5 from both sides, you get X. So the idea of working with functions is this idea of everything cancels out and you're left with X. So this is a very simple example, but the same thing happens if we were looking at something more complicated that we've talked about recently. Do you all remember that when we talked about log properties? Natural log of e to the power of x is x. Likewise, e to the power of the natural log of x is x. This is a different version of this. You start with the operation base e, you perform the log base e, you get x. You start with the operation log base e, you do the operation base e to the power of x, you get x. So this is the idea of functional inverses. There is a very particular type of inverse that some of you are calling inverses because of this obnoxious notation. And I say it's obnoxious even though it's universally accepted because it confuses people. What I mean by that is, let's say we have x and we multiply by 5. what is the inverse? Or what do I do to get x back? Well, you'd say you multiply by 1/5. And we know that 5 to the negative first power is 1 over 5. So this is kind of where I think that that function notation inverse comes from, is this idea, okay? But this is not the inverse. This is a very particular inverse. This right here is the reciprocal. And the reciprocal is the specific inverse that applies to multiplication. So going back to the beginning, if I have a point 4,5 and the inverse says, well, you should have the point 5,4 in the inverse, that's not reciprocating. You could think of it as reversing. You could think of it as swapping. You think of it as the old switcheroo. Those are all cool. You cannot think of that as a reciprocal. In math, the reciprocal is precisely this inverse. That is 1 and 1 inverse only. Okay, so let's do some practice. I've given you something that you should be able to sketch the inverse of using only the information you know about inverses. I don't want you to write equations. I don't want formulas. I don't want any of that. I just want you to think conceptually about what this inverse would look like. And then I want you to try sketching it. So you came up with the sketch. Mine's going to be in red. Here was my sketch. So something you may have noticed was the very first thing that I did. The very first thing that I did was I looked at the graph and I said that the graph of f has an input of 0 and an output of -3 and an input of 4 and an output of 0. And what I did was I said, okay, for f, I have 0, 3. For f inverse, I must have -3, 0. For f, I have 4, 0. For f inverse, I must have the point 0, 4. And this is a line, the inverse is a line. We can look at the same kind of thing here algebraically. So graph, table, algebra. It would be fair to say that f of x is the function that is a line that has a y-intercept of -3 and a slope that is up 4 and right 3. So I'm just going to write this in slope-intercept form, even though I normally do not. All right, I got that from the graph. I could do the same thing for f inverse. Okay, that's also a line. This one has a y-intercept of 4 and a slope of, oh, I wrote my slope wrong. I'm so sorry for confusing you. That's up 3, right 4. I was thinking about the inverse. Try not to ever be a step ahead of yourself when you're doing math. Okay, so that one is up 4, right 3, slope 4/3, slope 3/4. Perfection. Okay? Now, something that happens a lot, and this is just a notational thing, but a lot of times you'll see this when you're doing your calculus, is they'll say some other function is the inverse. They'll name it something else. Mostly because they recognize that this inverse notation, I think, is confusing and nasty and tricky. And honestly, math should come up with a better way. Anyway. I just spelled slope with a T. Let's talk about the slope of f. That's f prime. Okay, so let's talk about x values, and let's talk about slope values. That's f prime of x values. Let's just start out at our 2 points, 0 and 4. Go ahead and say out loud in the privacy of your own home what the slope of f is at x equals 0 and x equals 4. Twas the same, was it not? Twas the same, both 3/4. Okay, let's choose some other points here. How about E? Ew. What's the slope at E? How about at pi? Double at U. You lied to yourself, pi is yummy. Okay, how about the slope at E and pi? 3/4. Sorry for the weird jump in the recording. I had a disconnect. Anyway, I was told I left off talking about the slope of f, which again was f prime, and we noticed that for every x value, the slope is 3/4. That's a line, that makes sense. So we looked at, or I looked at, and now you are, -2, 3/4. Doesn't matter which values we choose, the slope's always gonna be 3/4 for that line, correct? Correct. So where I was going next was talking about the slope of f inverse of x. And remember, f inverse of x is often going to be just referred to as a new function like g of x. So what I'm telling you is that this is a really good thing to write down all the time. Anyway, what I wanted to look at was the notation for the derivative of f inverse. So we start out by writing f inverse, and then we put parentheses and write prime. So that is the notation for writing f inverse prime of x. And it's really pernicious because it sure looks like times, doesn't it? But that is the notation that we have when we write f inverse prime. That's often why it's preferred to just say g is going to be the inverse of f. Okay, so same activity. We're going to do x, and let's practice our notation for f inverse prime. We know it's g. So we write f inverse, parentheses around f inverse, prime with an x. Okay, so that's our table. And remember, F inverse prime is probably going to be referred to as G. Oh, I forgot to write G prime over here. I'm so sorry. I'm still a bit off from the disconnect. Okay. So let's look at the same things. Let's look at we're not going to do those first. We're going to do these two later. Save it. Let's talk about E. What is the slope of the inverse at E? How about at pi? How about at -2? Slope for all of these is the same. It's 4/3. Look at the graph. It's a line. Dur. Now, I'm not going to use 0 and 4, although I could. I'm going to use -3 and 0 in exactly that order. And that's because there's an important connection that we need to make when it comes to finding the slope of the inverse. So see if you can puzzle out what it is already. Okay, we'll go back to the land of equations because I know you guys like equations. So we looked at a graph, we looked at some tables, let's do some equations. Do you all remember doing the old switcheroo in good old pre-calc where you'd switch your x and y's and solve for y? Remember doing that kind of thing? Yeah? All right, so add 3 to both sides, multiply both sides by 4/3. You'd have y equals 4/3 times the quantity of x plus 3, which is super close to what I was expecting for F inverse. And exactly, if I distribute 4/3, I get 4/3 times x. 4/3 times 3 is 12/3, or 4. La di da. All that sweet, sweet algebra right there. Okay. Now, this isn't a super interesting question because the slope is constant. We knew that right from the beginning. F prime was 3/4. F inverse prime we can figure out is 4/3. So there's a relationship between 3/4 and 4/3, right? Yeah. That relationship is reciprocals. Not inverses, not opposites, none of that. Those slopes are reciprocals, okay? So I need you to remember that because we're going to look at a different function. So same directions. I want you to sketch what I'm going to picture for you. I don't want you to look at doing the equations or any of that. We'll come to that later. I just want you to look at the sketch and I want you to give it your best try. So the inverse, that's what you're after. Oop. I will tell you that's 0, -1. Okay, so no equations, no thinking about equations, no writing formulas, no doing tables, none of that. Just want you to sketch what the inverse looks like. Okay, so maybe you picked up on my other thing before and you at least did this. You knew that the inverse was going to be at the point -1, 0. You knew that. Did you draw something like that? Okay, I hope so. That's both good and bad. Why is it good? Well, it's good because you have the general idea down. That's what the inverse looks like. It's bad because that's not a function. Look at that thing. There we go. Our old friend, the vertical line test. Coming back after its appearance for implicit functions. Check it out. That is not the inverse function, is it? No, it's not the inverse function. How come? Because it fails the vertical line test. So we will talk more about this in detail in the future, but there is a thing called the horizontal line test. That is actually a test. Yes, that is a horizontal line of stars. You're welcome. That tells you whether or not a function is invertible. We're not going to spend a whole lot of time talking about that because that's pretty far deep in the weeds. But the main thing we're going to look at here is we're just going to say that we're only looking at this one. Okay, so that's all we're going to be talking about. Just that part right there. Just to make our life easy. And we'll spend more time talking about the inverses later when we talk about trig inverses. Anyway, looking at the table, f of x, when x is 0, f of x is -1. So we know if we're doing the inverse function, f inverse of x, which you could call g, the reverse is true, -1, 0, right? Right. And then we know that the shape should be the same. Now, it would have helped a lot if I had given you more points, okay? So I'll just say that the points 1, 0 and -1, 0 were part of that. So 0, 1 and 0, -1 are part of f inverse. Okie dokie. All right. So if you had to write an equation for f, you'd probably come up with that. Or maybe you might do x minus 1 times quantity of x plus 1, whatever. We'll do that. Okay. So I hope you'll forgive me. I'm not going to do all of the algebra, but it comes from the same place for what I did in purple, and writing y for f of x, switching, solving. I didn't write that in the right color. I apologize. F inverse of x is, again, we're just going to look at the positive square root of x plus 1. All right. So we have something much more interesting here if we start trying to do a slope table. All right. The slope, f prime, is not the same value every time, is it? No. We know that's true because it's a curve. It's got a different rate of change. Okay. F inverse prime, likewise, the slope is not going to be the same value, every single value of x. F inverse prime, I'm just going to do it and simplify it for you. Sorry if you're offended. I took away your opportunity to take a derivative. But we don't want to take all that time. Ooh, I forgot twice to write equals g of x. I apologize. Okay. Same thing, we're going to do a table of the slopes of f and f inverse. Remember, f inverse with parentheses prime of x, that's the notation that we use. And that's also g of x. Okay. And we're not going to look at every point here. We're just going to look at a few points in both cases. All right. So which points are we going to look at? And it's deliberately confusing that I used 0, 1s, and -1s here, because I want you to think really careful about what we're doing. So let's talk about exactly that. For f, the slope at 0, the slope at 1, the slope at -1. We could do it on the graph, sure, but we got this formula here that we're going to use. So f prime of 0 is 0, f prime of 1 is 2, f prime of -1 is -2. Now, do you remember in the line how I was obscurely difficult? Yes, I used 0 for both f inverse and f, you remember that? But I didn't line them up the same way. Did you notice the pattern I lined them up in here? Let's look at the graphs and the tables. I deliberately paired up these points together. 0, -3, and -3, 0, 4, 0, and 0, 4. So the input of 0 for f lined up with the input of -3 for f inverse, which, by the way, was the output. Same thing here with 4 and 0. I'm going to do the same thing with f inverse prime and f. So I'm not going to match 0 to 0. I'm going to match 0 to the corresponding x value in f inverse, which is -1. Likewise, I'm not going to do 1. I'm going to do 0 because 0 is the corresponding value in f inverse. And then finally, I'm not going to do -1 here. I'm going to do 0. Which is weird, right? That's mega weird. I got the same input. That's super confusing, isn't it? That's why we have to restrict ourselves to just this one. Okay, so let's talk about the slopes. Looking at f inverse, that should say g prime. Sorry. What do you get when x is -1? -1 plus 1 is 0. Square root of 0 is 0. This is undefined, isn't it? Okay. How about when x is 0? What do you get? You get a half. We said with the lines, the slopes are reciprocals. Do you agree here that the slopes are reciprocals? Sure look like it, doesn't it? So they're not inverses, they're reciprocals. But life can't be that easy, can it? No, it cannot. Let me add on a couple of additional points to hopefully drive this idea home. It's not just that the slopes are reciprocals. The slopes are reciprocals. What's a good one? Yeah, let's do 2. Okay. The slope at 2 is 4, right? Now, you cannot just write 2. How come? Well, if we go back to x and f of x, when x is 2, What is the output? According to our formula, 3. That means in the inverse, it's 3, 2. So it's not 2, it's 3, because 3 is the inverse value for 2. So what's F inverse prime or G prime of 3? 3 plus 1 is 4, square root of 4 is 2, 1/4. What would have happened if I used 2? If I used 2, I would have had 1 divided by 2 times the square root of 3. Is 1 divided by 2 times the square root of 3 the reciprocal of 4? Absolutely not, no. So it's not just that the slopes are reciprocals. The slopes are reciprocals at the inverse points. So that's why we have to be so careful with the words inverse and reciprocal. Okay, the same thing persists. 8. 8 seems like a good one. Okay. F of 8 is 63. So in the inverse function, it's 63 with 8. Watch what happens. The slope at 8 is 16. You can't use 8 here because if you substitute 8 into this, you don't get 1/16. No. You get 1/6. So it's not 8. It's got to be the point that is the inverse, not the reciprocal. The inverse of 8, the output. That's 63. Check 63. 63 plus 1 is 64. Square root of 64 is 8 times 2 is 16, 1/16. So, inverse functions. And functions have reciprocal slopes at, I'm going to use the phrase inverse. But what I mean by inverse is when you switch your input and output.